Okay, so we introduced cell potential and standard cell potentials. They are, they essentially are like, they're measured as the driving force of an electrochemical reaction. And what I mean by driving force is how likely is this redox reaction to happen, right? How favorable, how energetically favorable is it? And so we can get an indication of that by measuring something called the standard cell potential. So think about it. If you want to use, let's see, an application of a galvanic cell is for a battery, right? Or let's say you want to light a light bulb. You want to do some type of work from this redox reaction. Well, you want to get a sense of, okay, the redox reaction that I've made a galvanic cell on, how how good is it, right? Um, how favorable is it? Am I using, so we know if it's a spontaneous redox reaction, which it has to be by definition to make a galvanic cell, this is favorable because we don't have to put in any work, and we're able to harness those electrons to carry out some work, but we don't have to put in any work for the reaction to go. But to get a measurement of how favorable it is, this is what is the standard cell potential. So this value is going to depend on the nature of the redox reaction and the concentration of the species that are involved, right? The oxidizing and reducing agents that are present, the electrolytes that are present, right, in each half cell. So just like with other, right, when we looked at different thermodynamic properties under standard conditions, these are the standard conditions by which we measure standard potentials, right? At 1 molar concentration, if we're looking at gases, the pressure is 1 atmosphere, temperature is held constant, usually at 298 Kelvin. And the units of our standard cell potential is going to be in volts or millivolts. So here's an example of a redox reaction that we could use in a galvanic cell. So we have zinc being oxidized and we have H plus being reduced. So the standard cell potential for this redox reaction was found to be positive 0.762 volts. Now, when we measure the standard cell potential, this is for the entire redox reaction, right? We cannot measure the standard cell potential for a half reaction. We cannot measure it for only the oxidation or the reduction. It is for the entire redox reaction. And the way that we do this is we have a standard reduction potential that has already been set. And this standard reduction potential is called the standard hydrogen electrode, whose acronym is SHE. So the reduction of H plus ions to hydrogen gas has been assigned 0 volts. So we can couple this to any other, so this is one of our half cells. We can couple it to an oxidation, any other oxidation reaction, and this is how we are able to get the standard cell potential for the overall reaction. So just like cell potential, right, our standard cell potential is calculated in the same way. We just have E naught, right, which indicates that this is happening under standard conditions. All right, and as I just mentioned, so this is the standard reduction potential value of all half reactions are assigned relative to SHE. are all assigned relative to She. So they're coupled with the standard hydrogen electrode half reaction, and we're able to get a standard reduction potential value. And so the anode, the standard reduction or the standard potential at the anode is subtracted from that of the cathode because oxidation is the reverse of reduction. So if you write the oxidation step, the reduction step, right, and then you add them to get the overall the overall redox reaction, you would simply add the standard cell potential values. But oxidation is the reverse of reduction. So the signs at the oxidation step would actually be reversed. And in reversing that, it's the same as subtracting the anode from the cathode, right? Because a negative minus a negative is going to give us a positive. So it's the same as adding the standard cell potential of the reduction plus that of oxidation, or subtracting the standard reduction potential at the anode from that of the cathode. So here's an example of where there's a galvanic cell created to measure the standard electrode potential for the reduction of copper, So here's our standard hydrogen electrode, and these electrons from this reaction are able to flow to our cathode where copper is being reduced, right? Where copper 2 plus is being reduced to copper solid. So this is an example of how in this next slide, when I show you all of these values of different half reactions, this is how we're able to get these standard reduction potentials or standard cell potential values by coupling them to this standard hydrogen electrode. So here is, I think it's Appendix L maybe in your textbook. I will always provide you with the standard reduction potentials, right, on an exam. So these are standard reduction potentials for different half reactions, right, for reduction half reactions. And we were able to get these values because they coupled them to the standard hydrogen electrode, right? They coupled them to She. So if this reaction is, let's say we look at an example where we see that cadmium is actually oxidized, it would just be the reverse, right? Oxidation is the reverse of reduction. So in that case, this value of negative 0.403 would become positive 0.403, right? So standard cell potential is the same as standard reduction potential, and they are called standard reduction potential because when they were measured, they were all measured for as a reduction half reaction.